Okay, so we're going to be talking about one of the transformations. This one is translation, which means to slide the shape. So transformation is a type of rigid transformation, which means it doesn't change the size. So the size stays the same. So let's look at this first example here. So the UTS, this triangle here, is our pre-image, meaning the original shape. And we're going to translate this shape up to this position, U prime, T prime, S prime. So let's record first the coordinates of these vertices. So this U here is -5, -4. So this is U. And then T is -1, -1. Let's actually go back. We'll do them in order here. STU. Sorry about that. So S is at 0, -2. And then T is -1, -1. And then U, like I said, -5, -4. Great. So now, let's look at so we're going to translate this shape to this position. So the U will move to the position of U prime, T will move to T prime, S to S prime. So let's look at those coordinates. So S prime is 3, 4, and T prime is 2, 5, and U prime is -2, 2. So the way we're going to describe this translation is to describe how the shape moves. So we can choose any point, and they all move the same amount, the same direction, right? Because translation maintains congruence, meaning this shape is exactly like this shape. So each point has to move exactly the same amount, or else the shape would change somehow. It wouldn't be the same shape. So if we look at how the point S moves to S prime, that's going to be the same as how T moves to T prime and U moves to U prime, or any point really. This point moves to this point. So if we look S to S prime, S moved 3 to the right, right? That put it right underneath it. So S moves 3 to the right, and then 1, 2, 3, 4, 5, 6 up to be in the position of S prime. So a description of this would be, for example, move 3 right, and we said 1, 2, 3, 4, 5, 6 up. So that's like a verbal description, or just a description of the move. If we want to represent that algebraically, we can think about what happened to each of the coordinates. So we know that the x coordinates represent left-right movement or left-right position, and the y coordinates or y-axis represents up and down. So if we think of 3 to the right, that's the same as taking whatever x coordinate we had before, so in this case 0, and move 3 to the right. It'd be like adding 3 to it. 0 plus 3 would be 3. So we can describe this move as x plus 3, meaning whatever x was before, 0, add 3 to it, 3, and that's going to be the new x coordinate, right? This one was 0, -2, and this is 3, 4. And then we can do the same with the y. Moving 6 up would be taking whatever the original y coordinate was and adding 6 to it. So that would be going 6 up. So we can represent these by saying like something to the right or left and up and down, or we can say the x coordinate and add or subtract a number, and y coordinate and add or subtract a number. So this description should work for all the coordinates. So to describe this move, it should be the same for t. So if we think negative 1, right, that's our original x, plus 3. Negative 1 plus 3 is 2. And our original y coordinate, negative 1 plus 6, would be 5. And same thing here. If my original u x coordinate would be negative 5 plus 3 would be negative 2. And that's where that ended up, negative 2. And then negative 4 plus 6. Negative 4 plus 6 is positive 2. And that's the new y coordinate of u prime. So this describes the move x plus 3, meaning 3 to the right, and y plus 6, meaning 6 up. So let's show one more example of that. So here's our original or pre-image, JKL, triangle JKL. So if we want to describe this translation, we can record these coordinates. So the coordinate of J would be 3, 4. And then K would be 3, 5. And then L would be 1, 5. And so this shape is going to translate, right? Slide left and down. You can see it goes left and down. And actually, let's describe the move first, and then we'll record those coordinates. So this, like, just choose any point and move it to the corresponding point. So K is going to move to K prime. So for K to go to K prime, it would move 1 left. So 1 to the left. Move that up a little bit. 1 to the left. And then, so K to K. Don't move to any other point. Go from K to K prime. So 1 left, and then 1, 2, 3, 4, 5, 6, 7 down. So left on the x-axis, that would be like subtraction or negative, and down on the y-axis would be negative. So we could describe this move. Just zoom out just a little bit, sorry. There we go. So if we were going to go 1 left, that would be like taking the old x-coordinate, right? Whatever k's x-coordinate, in this case 3, subtracting 1 from it. Oops, these are supposed to be negative. My apologies. All right, that should be negative 3, and negative 1. So sorry about that. Make that correction. Negative 3, negative 1. So, like I said, these x-coordinates, let me correct those. So the original position of k, negative 3, or j, negative 3, 4, k, negative 3, 3 to the left, 5. So x minus 1, this is 1 to the left, and y minus 7 is 7 down. So j prime, right, if I take the original x and I subtract 1, so negative 3 minus 1 should be negative 4 here. Now let's check. J prime, right, 1, 2, 3, 4 to the left, yep, negative 4, good. And then j was at 4. If we do 4 minus 7, that would be negative 3. And we can see that j is at negative 3. So you could count the spaces, right? It's going to go 1 left and 1, 2, 3, 4, 5, 6, 7 down. Or you could subtract from these numbers or add to these numbers to find the new coordinate. So k prime, right, will be located at negative 3 minus 1, which is negative 4. And notice I'm not even going to the graph, I'm just using the numbers. And 5 minus 7, negative 2. Now let's check that. K prime should be at negative 4, negative 2. Negative 4, negative 2, there's k prime. So it worked. Let's do the same with L prime. So L prime should be, L was negative 1. Negative 1 minus 1 would be negative 2. And L was at y coordinate 5. 5 minus 7 is negative 2. So that means L prime should be at negative 2, or 2 left, 2 down. 2 left, 2 down, there it is. So just shows that we can describe translation as adding or subtracting from the original or pre-image x and y coordinates. Notice that all the points moves the same amount. This is really important, right? Because this shape is congruent to this shape. So J moves 1 left and 7 down, so does K, so does L. They all move the same amount, so they maintain the angles, they maintain the side lengths. So just a quick review of kind of the facts about translation, right? It proves congruence because all the points move exactly the same amount, so it says keeps the same side length, same angles. The size stays the same. The orientation, meaning the direction it's facing, stays the same. The orientation of the vertices, meaning how you read them from like clockwise or counterclockwise. This is STU, right? Counterclockwise. S prime, T prime, U prime, also counterclockwise, so that stays the same. The shape is exactly the same size. Every point moved the same amount, so the side lengths are the same, meaning the length of TU is the same as T prime U prime. This length is the same as this length. This length, same as this length. The angles are the same. This angle T, whatever that measurement would be the same as T prime, same measurement. So the angle measurements stay the same. And if your shape has the same side length, same angle measurements of all corresponding sides, then it's congruent. So this proves congruent. The shapes are congruent, which is one of the key reasons to talk about translation, is to prove congruence.